Welcome back. Let's go ahead and talk about the steel ball demo drop on the board. Kind of explain what's going on there. All right, so what I'm going to do is I'm going to draw a little platform. So there's my platform. I'll just put a little shading in there. I like to do that. And there's the steel ball right there. And let's pretend there's two of them instead of just one. Now, we're going to give the one ball an initial horizontal velocity. So I'm going to use this red arrow to indicate that initial horizontal velocity. And let's say that initial horizontal velocity, and I'm just going to make this up, let's say it's 2.2 meters per second. But it could have been 3, it could have been 4, it could have been 100 meters per second. Doesn't matter, all right? Doesn't matter. And I'm going to call that V sub I sub x, the initial velocity, the initial horizontal velocity. So the one ball that was launched horizontally, I gave it an initial velocity. That's kind of where the experiment started, after the plunger hit the ball and the ball had an initial horizontal velocity. Now, that ball also was at rest vertically. So vertically, it started from 0, and then gravity began to accelerate it downward. So I had an initial horizontal velocity, and I have an initial, my initial vertical velocity is 0. Now let's take a look at the other ball that just fell vertically. Its initial horizontal velocity was 0, and its initial vertical velocity was also 0. And it fell straight down. So I'm going to indicate that with a dashed line going straight down. So this is the path or trajectory the ball that just fell vertically took. The other ball, which was launched horizontally, did this. This was the path it took. And that path, mathematically, that path is known as a parabola. A parabola. So back to this again. Now what I'm going to draw is I'm going to show both spheres falling at different points in time. So here's a point in time right there, and there's a point in time right there. Remember, this one represents the ball that was launched horizontally. This one represents the ball that was dropped vertically. And there it is, and there it is, and just before it hits the ground, and just before it hits the ground. Because after it hits the ground, the experiment's kind of over at that point. So the experiment begins after I gave that horizontal ball an initial velocity, and the experiment ends just before the two spheres hit the ground. Right, let's go ahead and give these spheres some velocity. So first of all, let's work with this one right here, the one that was launched horizontally. So I indicated this initial horizontal velocity using an arrow. And I made it this long. I could have made it longer, could have made it shorter, doesn't matter. Let's say that length represents 2.2 meters per second. Now, my question is, how long should I draw the horizontal arrow for the ball when it's at this position? Should it be longer than that arrow? Should it be shorter? Should it be the same size? Turns out, it's going to be the same size. So I'm going to try to draw a horizontal arrow the same size. And then I'm going to do it again, and I'm going to do it again. And the reason why we draw it the same size is because there are no horizontal forces acting on this ball if we neglect air resistance. In my little demo over there, air resistance was negligible, hardly anything at all. But let's go ahead and just totally neglect air resistance. If we do that, there's no horizontal forces acting on this ball. And remember, it takes a horizontal force to speed up or slow down an object, right? To accelerate an object. So no horizontal forces, and therefore this horizontal velocity stays the same. It's going to stay the same. All right, let's talk about the vertical velocity. Now, in both cases, gravity, a force, begins to accelerate or speed up the ball. And in both cases, gravity is pulling on that ball, right, out of those spheres, with the same force. And it's beginning to accelerate them at the same rate, 9.81 meters per second squared. So what I'm going to do is I'm going to draw a downward arrow to represent the downward velocity. Now this is where both spheres start, so no downward arrow because vertically they both started from rest. And then after gravity, begins to accelerate it, they got a little bit of vertical velocity. So both of these, same. And then I'm going to draw even a bigger arrow because that force continues to accelerate the ball, speed it up in this case. So my vertical arrow gets a little bigger. And then just before it hits the ground, that's where my vertical arrow is the biggest. And notice both of these vertical velocities, they're going to be the same, right? Because the same force is accelerating them. So just before they hit the ground, vertically speaking, they're going to be going the same vertical velocity. All right, now we're going to go a little bit further. And I've got two different velocities happening at the same time, right? Because it's motion in 2 dimensions. So this vertical velocity here, I'm going to represent that as v sub y. And the horizontal velocity, I'm going to go ahead and I'm going to call that v sub x, the horizontal component of the velocity. And if I want to know the total velocity, what I'm going to do is I'm going to vectorially add these two vectors, those two arrows together. Now I'm going to vectorially add them. It doesn't mean I just take this number and that number and add them together, because those arrows are not in the same direction. If they were, I could do that, but they aren't. So I got to do a special type of addition called vector addition. And graphically, we're going to kind of do this like this. I'm going to draw a dashed line, and then I'm going to go ahead and start here, and I'm going to connect it right there. And this arrow is going to represent my total velocity. So if I add this and I add that vectorially, that, if I had a little radar gun, that would be the number the radar gun would actually show, my total velocity. And you could do the same thing for this one, and the same thing for this one. And notice the arrow's getting bigger, bigger, bigger. And the reason is because this vertical part of the velocity is getting bigger, bigger, bigger due to gravity. This one, this is the total velocity right here. There's only one dimension to it. So this is motion in 1 dimension, and this is motion in 2 dimensions. And both motions are occurring at the same time. And the weird thing is we can actually treat those as 2 totally separate motions just happening at the same time. And because of that, we get this kind of curved path called a parabola. Now, let's go a step further and talk about the acceleration. So I want to talk about the horizontal acceleration, a sub x, the average horizontal acceleration. So horizontally speaking, how fast is that ball accelerating? And the answer is 0. Because what is acceleration? It's a measure of how quickly our velocity is changing. And the horizontal velocity is not changing. It's not changing. So it's going to be 0. Now vertically, let's take a look at the vertical acceleration. So acceleration sub y, right? There's a force. And that force is causing these balls to speed up. And it's speeding up at a rate of 9.81 meters per second squared. And it's speeding them up in the downward direction, because gravity always, always, always wants to pull an object downward towards the ground. That's right, so that's the acceleration. And that's the acceleration of both of these metal spheres in the downward direction, because gravity is accelerating both downward at the same rate. Now, let's take this a step further, and let's pretend I have two bullets. Two bullets. I got one bullet I'm going to hold between my fingers, right? One imaginary bullet I'm going to hold between my fingers, and the other one I put into a long rifle. And what I'm going to do is I'm going to hold that long rifle nice and horizontal, and I'm going to pull the trigger. And that bullet is going to end up, let's say, a mile away. It hits the ground about a mile away. And at the same time I pull that trigger, I take the other bullet between my fingers and I just drop it. Just drop it from rest. Which bullet hits the ground first? The thing is, it's going to be the same as the demo. They're both going to hit the ground at the same time, right? Because gravity is accelerating both bullets downward at the same rate. The bullet that was fired from the gun is also, as it falls to the ground, it's also moving horizontally. So what's actually happening here, if you think about my demo, if I had a stronger plunger and it could, hit the ball harder and give it a bigger horizontal velocity, let's say 4 meters per second, it would look like this. Again, a parabola. And if I could hit that ball even harder and give it a greater horizontal velocity, it would look like that. And it would look like that. And if I could hit it hard enough, like the long rifle, it would actually go a mile away, right? Let's just assume that when I drop the bullet, let's just assume it takes a half a second to hit the ground. Well, the bullet that comes out of the rifle will also take a half a second to hit the ground. And it's just a matter of how far horizontally that bullet can go in a half a second before it hits the ground, right? A stronger rifle will impart a greater initial horizontal velocity, and that will make it go further horizontally before it hits the ground. All right, great. Now, let's go ahead and kind of write two definitions down. So the first definition is motion in two dimensions. 2D, two dimensions, right? Because it's moving both vertically and horizontally at the same time. This is also called projectile motion. And it's also referred to as parabolic motion. So all three of these kind of mean the same thing, right? Motion in two dimensions, parabolic motion because the object makes or follows the path of a parabola. And projectile motion because that steel ball was a projectile, and we'll talk about that in just a minute. Well, let's go ahead and define motion in two dimensions. Right? So motion in two dimensions. When an object has two separate motions, when an object has two separate motions occurring at the same time. So it's got a vertical motion and a horizontal motion, and they're occurring at the same time. And that's why it kind of looks like it's going in a parabola, which it is, right? But you got two separate motions happening at the same time. Think about, well, let's go ahead and, before we do that, let's talk about a projectile. Let's define a projectile. A projectile is an object, or I should say when. Let's do that. When an object is given an initial force and then falls under the influence of gravity. All right, so an object is given an initial force. So a force is a push or a pull. So in our case, we gave it an initial boom, force. And then the problem started. That force set the ball, it gave it a horizontal motion, it gave it a horizontal velocity. And it doesn't have to be horizontal. It could have been an upward, velocity at a 45-degree angle or a 60-degree angle, but it's given an initial force, an initial push. And then that push ends, and the object falls under the sole influence of gravity. That object is a projectile. So an example would be any object shot or launched. Right? That could be a baseball, that could be a football, it could be a metal sphere like I did in the demo. It could be a golf ball, right? Anytime I take something with, let's say my hand, I put a baseball in my hand and I throw it, I'm applying a force to it, and once it leaves my hand, now it's under the sole influence of gravity. Again, if we neglect air resistance, right? So even a shot putter, right? That ball would be a projectile. A bullet would be a projectile, right? And in a not so great sense, think about projectile vomiting, right? Your stomach wants to get rid of some contents, and it squeezes those contents really hard. That's a force. And then as those contents come out of your mouth, now they're under the sole influence of gravity. Projectile vomiting, right? If you were to take a slow motion video of that, hopefully you don't, but if you did, your vomit would move in the path of a projectile, or the path of a parabola, all right? So any object that's given an initial push and then begins to fall under the influence of gravity is a projectile. Now let me ask you this, would a helicopter or an airplane be a projectile? And the answer is no, because the engine is constantly supplying a force. At no point is it under the sole influence of gravity. At least we hope not, right? Because you don't want to become a projectile, while you're flying in a plane. Don't want to do that. So a plane or a helicopter, not a projectile. A missile with fire coming out the end, again, not a projectile because it's given a constant force. However, what if we launch a satellite? That satellite is given a force until it gets high enough above the surface of the Earth. They call that orbit. And then the fire, right, the fuel runs out or stops, and now that satellite is under the sole influence of gravity. So a satellite, as it falls around the Earth, and we'll talk more about that with circular motion, that would be an example of a projectile. All right, so that's it for two-dimensional motion.